Okay, I think we can start. So, hello everyone. Here we have Antonis, and he's a software engineer at platform.ch, Docker captain, and passionate Python developer. And today he will walk us through the world of Django. So, please, the floor is yours.
Thank you very much, and thanks a lot for being here. In Vilnius, it's my first time in Lithuania, so I hope to enjoy the city a bit. So today we're going to talk about Python, async.io, which is the asynchronous library for Python, and how we can use it in Django, which is one of the popular frameworks. So before we start, let's make sure that everybody is woken up. So any Python developers in the room? Okay, I cheated a bit. Let's go to the second question. Any Django developers in the room? Okay, that was an easy one. And anybody here has used either for playing around or in production async.io, async.io? Okay, cool. So we have a few. So let's see what we're going to talk about. So a few words about me. I'm a software engineer at platform.sh, where we build a product called Apsan. If you would like to deploy your applications, feel free to go there. I'm a Docker captain. I code for Python for, I don't know, most of my professional career. I love it. I know people say it's not fast, it's slow, it's perfect. We love it, we know it, it's fine. And generally, I love the automation part. I want to see how we can help developers make things faster, how we can use our resources smarter, all those things. What we're going to talk about today. First of all, we're going to talk about concurrency and parallelism. There's a distinction there, which we should be aware of. Then we're going to talk about the event loop, which is the tooling that we use in order to have concurrency. We're going to talk about, of course, how we can leverage this in Python and Django as a context. And then we have a small demo, so we're going to see how we can take a Django application that was built traditionally, and then use that tooling to make it maybe a bit faster or perform better. So concurrency versus parallel computing or parallelism. Anybody here? I mean, who's like really knows, or I mean, feels that they know what's the difference between the two? Okay, just a few. So that's a good one because that's why you're here. So let's start with concurrency. So concurrency, if you take, I took this from Wikipedia. Concurrency is the ability to run different parts or units of a program, algorithm, problem, whatever. And those things, those smaller parts, can be executed out of order. You can shuffle them around, and then the end result will be the same. So you see here, there's no thing of running all the things at the same time. It's running bits and pieces, so breaking down your program so that you can run it in a way that at the end you will have the same end result. On the other hand, parallel computing is a way to execute multiple calculations. So programs are calculations, so instruction code and all those things, simultaneously. And pay a lot of attention in the word simultaneously, because this means that we have, for example, multiple CPU cores, and then we execute all those things at the same time, simultaneously, in parallel. That's the clear distinction. So concurrency out of the box does not bring us a lot of improvements. And in order to make this a bit more clear, let's see our classical examples, a serial execution. So we have 4 things to do, 4 Python functions to run. Let's say we have task 1, 2, 3, and 4. And then if we have just one CPU core, we execute it normally. Those things will be executed one after the other. So the first task will start, and then the second one, third one, and so on and so forth. If we go to parallel, which is the easiest thing to know, let's say now that we have 2 CPU cores, so we have a computer that is kind of faster. So we say, okay, we're going to execute task 1 and task 2 in CPU 1, task 3 and 4 in CPU 2, and then we have a lot of improvement in speed, because you see we have a lot of white space to fill with other things to run inside our program. Now, when it comes to concurrency, this can be a bit different. So if you remember, we said that we can, split the program into smaller units and then execute them out of order. And then at the end, we're going to have the same result. So let's say that those tasks could be run using a concurrent execution. We could start with task 1. Then at some point, we're going to stop task 1, continue with task 2, then back to task 1, then task 3, task 4, and then task 3 again. And then if this code is correct and is written in a way that is concurrent, at the end of task 3, we're going to have the exact same results. So all the tasks will be completed and we're going to have the same results. So concurrency does not necessarily mean that all those things run in parallel or simultaneously. It means that they can be run out of order. So the normal question that comes to mind is, okay, that's fine. Why do we care about concurrency? Why not just go with classic parallel execution where we can run all the things in parallel, have big machines with a lot of CPUs, and everybody will be happy? And that is a very good question. And the easy answer is, of course, not everything is easily parallelizable. I mean, you cannot take a code that takes 10 minutes to run and then make sure that it runs in 2 CPUs and takes 5 minutes, because parallelism means that you have to synchronize the state between the code parts that have a certain state. Maybe you need to share memory. Maybe you need to execute different processes and then have IPC, inter-process communication. So it's not very easy. I mean, if you happen to have any parallel systems class back in school or all those things, you remember that the moment that you wanted to execute all those programs in parallel, things were not as easy. It's not like, okay, I take this code and I magically run it in parallel. The other thing is, of course, in order to have parallelism, we need to have multiple CPUs. I mean, you cannot run many things simultaneously with one CPU. I mean, we can, of course, but this is how the operating system works, and it has a lot of hardcore engineering in order to make this work. But again, our actual program is going to be run serially, not in parallel. And of course, we need a lot of memory. So for example, if you remember, if you have run Unicorn in production, you know that in order to have multiple workers, you need to have more memory because each worker needs to have its own memory space. And then, of course, we have threads, so we can kind of share some of that memory and maybe reduce it a bit. But again, every different process is like a completely separate thing. It's not that we can share state or share things between all those processes. And of course, the reason that we're here today is that we can use concurrency and parallelism together, and this is how it's made to work. So let's see how we can leverage both multiple CPU cores and concurrency. So in the previous example of those 4 tasks, we can run things either in the first or the second CPU, and as you can see, we can even schedule things in different CPU cores because we can use parallel execution. So we have multiple things running our process, and then we can do things like that. So in order to do that, we need to go into our application and find the moments in time that we do not really need to be on the CPU for the program to run. If you are running something that is very compute heavy, okay, you have to be on the CPU, and it's not very easy to make sure that this runs at the same time. But most of web applications do things like database queries or hit other APIs, or they do a lot of things that for some time, for a few milliseconds, the application is not running on the CPU. It's not doing computation. So let's say that I do a database query, an API call, and push my logs to a server. All those things, if we annotate our code, let's say in a wise way, we can say for those moments, okay, now I'm going to go to the database. For that time, you can run something else instead of me. And when the database results come back, then I can continue running. So this is how we can use concurrency to make our applications that are not running on the CPU and have hardware interrupts run smoother and faster. And in order to better understand this, we need to understand what are the tooling that we have in order to run all those concurrent programs. First of all, we have a new notion. We call them coroutines. Coroutines in the previous examples were all these different tasks. So task 1, 2, 3, and 4 were different coroutines, which are like special programs that we can, schedule and unschedule from the CPU as we please. If we take the, official Wikipedia entry for this, coroutines are computer program components that generalize subroutines for non-preemptive multitasking by allowing execution to be suspended and resumed. So, okay, this is, maybe too serious, but the important thing is that those coroutines can be paused. So let's say I go to the database, I can be paused at that moment and then resumed. So resumed from the exact moment where I was. So, the exact Python line of code where I was, as soon as those database results come back to me. So for the time that I'm, querying the database, something else can run instead of me. The second very important concept in concurrent programming is what we call the event loop. The event loop is the program, let's say, or the programming construct as it says here, that waits for and dispatches events or messages in a program. So the event loop is the orchestrator that is understanding, okay, this coroutine is querying the database. Let's switch it and put another coroutine in its place. And when the results of this coroutine are back, I'm going to take those results and then send a signal to this coroutine to continue running. So the event loop is the orchestrator, and the coroutines are those asynchronous program pieces that we can run interchangeably and achieve this thing. If we put this in pseudocode, it would be something like that. So the execution would run. So we would start with coroutine 0 because we are engineers and we start with 0 all the time. Then at some point, the coroutine 0 would hit the network or something that creates a hardware interrupt, so it's not directly on the CPU doing computations. So we're going to remove it from the CPU, remove it from the execution loop, and then continue doing the same again and again. So run coroutine n, so 1, 2, 3, 4, whatever, and then remove it. And at some point, we are going to start checking. So as long as all the coroutines that we have in our list are, have paused running, then we're going to start checking results. So has the coroutine 0 received any results? If yes, put back coroutine 0 and then, continue running until it finds something that it stops again. Then go to coroutine 1, do the same. Coroutine 2, do the same. So the idea is that we have a very, very dumb for loop. Of course, it's more sophisticated than that. That goes through all the coroutines, starts running them. As soon as they hit a database query or something else, they pause, they go to the next one. And then when the results are back, the moment the loop comes back to the coroutine 0, it's going to put it back to running to continue where it is. So very simple, like that. In Python, of course, we need some base construct, which is async.io, which is the library that is implementing all these coroutines, event loop, and all the other nice things, and of course some things around it. Generally, it's standard since Python 3.4, although I would be honest and say that between 3.4 and 3.7, it worked, but it was not amazing, let's say. But since 3.7, we have applications in production, and I've been using it a lot. It's fine. I mean, I have not found any for the normal use case scenario. I have not found any crazy bugs and issues. It introduces two new keywords in Python. The first one is async for Python for function definition, so we can annotate that the function is asynchronous, so it can leverage all those coroutines and all those things that we've been talking about. And the second thing is await. So await is the moment that our program, our coroutine, is going to signal the event loop that, okay, this is something that might take some time. So let's say that we're going to await some database results. In that moment, the event loop will pause our coroutine, will pause our Python code. It's going to get our Python, database results, and then continue with something else that needs to run into our system. In the context of a web application, this is my first request coming in, hitting the database, then the second request continues running until it hits the database, and so on and so forth. And also we have the async.io library, which is in the standard library, which has a lot of nice utilities around all this asynchronous logic and code. When it comes to web servers, if you dive into how Unicorn and the other web servers in Python work, there is what's called WSGI. So this is I do not remember the acronym exactly, but the idea is that this is the way that you create a Python server. This is the interface that you have to define so that you can use and execute requests without knowing what web framework lies after you. In order to be able to support asynchronous code, we have ASGI, which is the asynchronous interface that was introduced in Python. And we can have servers implementing the ASGI interface, and thus allowing event loops, coroutines, and all these nice things to run underneath them. So the idea, and of course, as we go further, we start talking more and more about Django, but of course, this can be leveraged in other web frameworks that support asynchronous code. With Django, now that we have ASGI, so we can run Django with an ASGI server. So for example, if you have heard of Uvicorn, which is the counterpart of Unicorn, but for asynchronous applications, then you can take all those nice things out of the box. So first of all, Django has a very nice, so Django was traditionally built for non-asynchronous applications. So all the code in Django, and especially the ORM, the database queries and all those things, are built around that concept. So of course, it's a very big framework. Many companies use it. It's not easy to say one day, okay, tomorrow the next version is going to be async only. So whatever code you have written which is not async ready is not going to work. That would not be an option. So Django is doing a lot of gradual rollouts for the last 2 or 3 major versions, if I remember correctly, that is introducing more and more asynchronous ready code in the framework, where you can leverage all those nice things that we've been talking about. Of course, this it's not easy to switch an application from one day to the other. So the good thing about Django is that you can have blended asynchronous and synchronous code inside it. There is full support for synchronous and asynchronous views, so you can start implementing asynchronous code in your views one by one. So it's easy, or you can find all those parts of your application that are very dependent on database queries or API calls, and start changing your code there. And there is a wide variety of decorators, middlewares that are async ready. So you can use the same decorator either on an async view or a synchronous view, and then have everything running smoothly. As with everything in life, everything comes with caveats, and Django has a few caveats. So if you start dipping your feet into the asynchronous code, you have to be careful with those. Of course, when you are running both synchronous and asynchronous code in the same request, then you have some penalties. Of course, those penalties might be a lot smaller than the actual time that you wait for a database query, but still you need to keep in mind that switching from synchronous to asynchronous code has some penalties that you have to keep in mind. For example, if you have a view that does some computation, but then again hits an API in an asynchronous way, then you have to make sure that those things you need to make sure that the speed that you're going to get from this asynchronous code is not going to fail you later down the road. The ORM, which of course is the biggest part of an application, especially with Django, which models are an integral role in the applications, is still work in progress. There are many functions in the ORM which are prefixed with the A prefix, so you can have something like a get instead of get to get an object from the database, which is async ready. But again, underneath, it's not fully asynchronous. It's not asynchronous, all the way. So they're still working on it. There's amazing work being done there, but again, it's not fully ready. And the other thing is that middlewares might not be async ready. So if you have a middleware that's not async ready and then a middleware that is async ready, then you're going to go back and forth between sync and async. So middlewares are a very common place where you go to the first bullet point and then you have all this pain without understanding it. It's not code that you run, but middleware are in the request flow. So if you go from synchronous to asynchronous middlewares and back, then this gives you penalties without you not without knowing, but without it being very obvious. But again, just by running Django with an ASCII server, you get a lot of nice things out of the box without doing anything. For example, you have static file serving. A big problem with Django applications has been that okay, I have 8 unicorn workers. This means that I can have 8 concurrent requests hitting my server without the next one waiting. And static files were not a good idea to use those requests for. Now you can have file static serving without caring about having a CDN or whatever in front of your Django application. It's fine. You can have very cheap concurrency, although you have to be careful with database connections. That's the biggest, the first roadblock that you find whenever you run asynchronous code. You can leverage all this asynchronous code to have better resource utilization and use more of your CPU. You don't want to use like 5 or 10% of your CPU. You want to use as much as possible. And by running concurrent code means that you spend more time on the CPU and less time waiting. So you can use it more. And of course, as we talked about, everything can be gradual. So all the migrations can happen slowly as you go down the road. So demo time, we're going to see how we can leverage all those things that we've been talking about in a very small Django application. If you would like to get the code afterwards or now, you can go to this link. It's publicly available on my GitHub. And let's see what we have here. So is it okay in the back, the size of the letters? Good. It was good, or like this, okay. Better? Good. Awesome. So I'm using a framework called Nano Django, which is something like a wrapper on top of Django that you can have everything in a file. So if you, do not pay a lot of attention in the syntax. Is just to make things easier and in a file. So I have a few settings. Nothing to see here. I have a model called conference and a model called talk. Which is getting all the conferences and the talks from previous PyCon Lithuania. I have a schema to create my API. And then I have get conferences and get talks. Actually, let's go to the main branch where we have the slow code. So we have get conferences and get talks, which just sleep for 2 seconds before returning the results, because I did not want to put like 1 million conferences just to make things slower. So if I go here and I hit the API, it's going to wait for 4 seconds, because first it's going to go to the conferences and then to the talks, and then I'm going to get a list of all the talks and conferences. So nothing crazy here, but I have a very simple application that, because of external factors, because of a slow database or because of an external API, my application does 4 seconds to return. Now, if I start hitting this application a lot, I'm running Unicorn here with 4 workers. So if I do 4 requests, the 5th one will wait for all the other 4 before continuing. So it's very slow. And actually, let's do a load test that I have here. So this load test is going to get first. This is my deployed application using the slow Unicorn implementation with a very small concurrency. So I'm just getting 8 parallel workers hitting my application, and it's going to load test it for 10 seconds. Of course, it's a bit slow, and with conference Wi-Fi, things might not be as expected, but let's see. I managed to get 17 requests in, so not a lot. And I have 5 seconds as the minimum response time and about 8 seconds average. So as you see here, we can, even our application takes just 4 seconds to return, we have a lot of wait time because, you know, next requests are waiting for the previous ones to complete. While if I go to the other one, you see that I have a lot smaller time in the response times, and of course here I have a lot of network issues, so you see a lot of slowness because of that. But the idea is that I can get more requests in just because those next requests are not waiting for the previous ones to go on. And before closing, let's go and see what are the changes. So a simple change without doing anything. This is the configuration file for deploying applications. Do not pay too much attention to the others. It's just changing from unicorn to uvicorn. So just with a simple change, I could get a speed up without changing no line in my application. So only thing I did was this, and okay, a small one, which was to add database connection pooling to make sure that I do not overuse my database. And then for that, I can start changing my application gradually. So for example, here, I can start switching from synchronous to asynchronous code, utilizing async IO, and doing all those nice things so that I can start doing this gradually with my own pace. And I'm out of time. So thanks a lot for being here. If you would like to discuss this, I will be today and tomorrow around here. So feel free to grab me and find this, nice t-shirt that is easily visible if you would like to talk. Thanks a lot.
Thank you, Antonis, for a nice presentation.
Thank you.